Hello. So after a long time we'll again continue with this. So let's start. So we will start talking about variance today. Okay. And let's begin. Okay. So how do we start with variance? And initially, what do we even need variance? Okay. So let's say I have a W. So let's say I have W, which is, let's say, at 0, at x equal to 1. Okay, so not x equal to 1, so sorry, it's like when probability is 1, so like W will always give 0. Let's say you have Y, which will give -1 and 1. -1 when it is at half, and 1 when it is at half, as in means half of the times it will give -1, half of the times it will give +1. Okay, now let's talk about some Z. So it will give you -100, 100 half of the times, and -100 half of the times. So if you find out the expectation of each of them, right, for the initial thing, the expectation will be how much? 0. The second thing will be what? -half plus half, that is 0. And finally also it will be -50 plus 50 is equal to 0. So for all the cases it's 0. So we don't get the essence of everything we are doing, right? We don't get the essence of, let's say, why, how expectation works usually. Okay, so now let's say we there is a huge spread here, right? So one is from, let's say, one is just here, another one is here, the another one is very off, like very far. Okay, so it's very far, so you cannot possibly understand this. So what we do is that we try to now do e to the power expectation of x. Instead of expectation of x, we try to gauge what expectation of x, how far is it from the mean. Okay, so and we don't want to deal with positive and negative values, so we actually take the square of this. So it becomes x minus mu whole square. So this is something we would want. Okay, this is what we call as, in essence, variance. Okay, so this is what we would want. So like we want x to take on values around its mean, so that it is like a possible way of measuring a possible variation of x. Okay, and so end of the day, this is what in essence variance is. Okay, so we can formally define variance as, if x is a random variable with mean of mu, then var of x is nothing but e to the power x minus mu whole square. Okay, so we can alternatively also find a formula of this. How can I find this formula? Wait, yeah, how can I do this? So let's expand this. Okay, so what does this formula come out to? This is summation of x minus mu whole square p of x, right? We did this in expectation. So if we break this down, this become x square minus 2 mu x plus mu square px, right? So this is what we have. Now finally, if we break it down, we get summation of x square px minus 2 mu x px plus mu square px, right? So this finally comes out to be what? Summation of x square px becomes what? E of x square minus 2 mu is your mean and p x summation. So like summation of, summation of px. Okay, so summation of summation of x px is what? Summation of x px is nothing but e to the expectation of x, right? So, and expectation of x is nothing but your mean, right? So we'll come back to this. So and this will become expectation of x whole square plus, okay, plus we have mu square summation of px, and summation of px is what? This becomes mu square only because summation of px is always 1 over all the values. So mu square is what? You find this out to be expectation of x whole square, right? Finally this value comes out to be what? E of x square minus e of x whole square. So this becomes my variance of x. This is my new formula, variance of x. Okay, so like let's do an example. Okay, so for a dice, find var x. Okay, so how do you find this one? So it will be nothing but first find e to the power x square, right? What is e to the power x square? This will be 1 by 6 into 1 square plus 2 by 6 into 2 square and so on. Okay, so this comes out to be, if you calculate it, not 2 by 6, sorry, 1 by 6, 1 by 6 into 2 square, sorry, that's my mistake. And this comes out to be total 91 by 6, and in last time we calculated e to the power x to be 7 by 2. So my var x will come out to be 91 by 6 minus 49 by 4, which is around 35 by 12. So this is how we can calculate variance for any case we want. Now let's talk about a very important property of how variance works. So one very important property is this: variance of ax plus b is equal to a square variance of x. How do you do this? What is the intuition behind this? So initially just start with e of ax plus b, right, minus 2, sorry, not minus 2, minus a mu minus b whole square, right? So what is the formula? X minus mu whole square, right? I'm just doing this. I'm putting the value of x. I'm putting the value of x and I'm putting the value of mu. So this becomes what? E of this, you'll find out b gets cut, then it will become what? A square x minus mu whole square, right? And finally it will be, I can take this out, okay, so this becomes e x minus mu whole square. So that's what? A square var of x. So this is a very easy proof of how this thing comes about. So with this, I didn't explain variance in that much detail, but this is the basic understanding of how variance usually works. So now we are going to talk about a very important thing, that is binomial random variable. Okay, this is a very important thing and we are going to discuss about it. So like suppose you are doing an experiment here right now, and so this experiment can either be true or maybe it can be false. Okay, as in like either you'll win or lose, so it's like a binary case here. Okay, so obviously it is very obvious. So let's say I'll name win as 1, loss as 0. So if I give you this case where p of 0, what is that? That is nothing but p of x equal to 0, right? And p of 1, that is nothing but p of x equal to 1. So let p of x equal to 1 be some value of p, then of course this has to be 1 minus p. It's like obvious because total probability is 1, right? So if we have only two choices, 0, we have two choices, 0 and 1, we cannot choose anything else, right? So this kind of variable x is what we call a binomial random variable. This binomial random variable is also called Bernoulli random variables. Okay, so okay, so if you get this mass function, you're going to get a Bernoulli what do you call it, Bernoulli random variable. Now let's say this is only for like one trial, right? This is for one trial. So now let's say if we are having n independent trials, okay, you're having n independent trials in which some might be p, some might be 1 by p. You have to realize ki this one is only for one case, right? So what is the probability of 1? Let's say 1 by 3, then the probability of 0 will be 2 by 3. This is one case. So this is what you call Bernoulli. Okay, this is what you call Bernoulli random variable just in one case. But let's say now we are going to n independent trials, right? So now there will be n experiments. Okay, so n experiments. Okay, so now this x will be called a binomial random variable, and it will have two parameters, n and p. Okay, so n and p's probability mass function will be given as p I is equal to n c1 I p to the power I 1 minus p to the power n minus I. Okay, so like how am I getting this logic? How did I get this out of my brain randomly? So in this, n is the total number of trials, p is the probability of 1. So probability of 1 is your p, probability of 0 is your 1 minus p. So how do I get this? So let's say p of I means what? Here x is equal to I means I have gotten I ones and n minus I zeros. Okay, that is the simple logic of this thing. So if I ones and n minus I zeros, that means we have to, since all of them are independent, we can do this. So p of AB is equal to p of A into p of B, right? So if there are I ones, so it will be p into p. How many times will this happen? I times. And 1 minus p, how many times? N minus I times. Okay, so now finally what do we get? P to the power I 1 minus p to the power n minus I. Now can you tell this will always happen like all p's at first, all 1 minus p? No, you have to do some combination among itself, right? So that becomes total number of things by how many are we arranging, that is the p times, right? So it's basically the 1 minus p is there, we need to insert IPs in these spaces between 1 minus p, right? Simple logic. Okay, so there might be 2, there might be 3. So how many spaces do I have for 1 minus p? N spaces will be there. How many p's do I have? I will be there. So total n c I. Okay, so this is how I get the formula for pi. So this is the simple logic for Bernoulli, and so this is binomial. So Bernoulli is basically, Bernoulli is what? Bernoulli is nothing but this thing only, but for 0, not 0, sorry, for 0 and p, sorry, 1 and p, 1. So n's value is 1. So then we call it as Bernoulli. Okay, so like let me give you a very good example, is that there are 5 coins, okay, tossed. So now what is the probability mass function of all the heads? Okay, simple logic. So first there will be probability of 0 heads. Okay, what is the probability of 0 heads? Formula 5c0, half to the power 0, half to the power 5. So that is 1 by 32. Okay, p of 1, 5c1, half into 1, half into the power 4, that is 5 by 32. And p of, you can calculate all of them. I'm just going to tell you the values. 10 by 32, p of 3 will be 5c 10 by 32, p of 4 will be 5 by 32, and p of 5 will be 1 by 32. So add up all of them. 1 plus 1 2, 2 plus 10 12, so 12 plus 20 is your 32, right? So we are covering all the cases. See, all the cases are covered. So you can see this clearly works. Okay, so this is what the base of binomial random variable or Bernoulli random variable comes out to be. Now we will try to find out how do we find out the expectation and variance for a general case. Okay, so for that we need to inspect this variable. Okay, e x to the power k. Let's inspect this. So by according to the formula, it should be nothing but, in this case it should be summation of x to the power k px, if I'm not wrong, right? So here we will just not write x, actually put I and summation of I. So this will become summation of I to the power k n c I p to the power I 1 minus p to the power n minus I. Okay, now we know I n c I can be written as n into n minus 1 c I minus 1. This is a property, you can prove it easily. So that using this, we will be using this here, and then what will we have? Summation of I n minus 1 c I minus 1 I to the power k minus 1 p to the power I 1 minus p to the power n minus I. We will take this n and 1 p common. Okay, so how can we do this? So, and we will take some value j to be I minus 1. We will replace the value. So we'll take np common, summation of j minus 1. So this will remain j itself, just j will be from 0 to n minus 1 now, and this I will become what? J plus 1 to the power k minus 1. This one will become n minus 1 c j. This will become p to the power j. This will become 1 to the p n minus 1 minus j. So this becomes my total formula. Okay. Now if you notice, if I take this as n, wait, so this is n p, this whole term, can we shorten this in any way? So like if you see, this becomes some e of y plus 1 to the power, sorry, to the power k minus 1. Okay, where y will be a random variable with what, n minus 1 parameters and p. So see, p is satisfying, and then n minus 1, and here n minus 1 you have, see, take this n minus 1 minus j n minus 1 cj. So this is your py, and here j plus 1 to the power k minus 1, this is your that thing, what do you call it, x to the power k. So we did a y plus 1 here because of that thing, and so this one becomes your final thing. Now let's see for let's take the value of k equal to 1. Okay, if k is equal to 1, then we will find out e to the power ex, right? Ex will become what, np into e to the power y plus 1 into 1 minus 1. So this becomes 1, is the whole value is 1, e to the power 1 is always 1, so this becomes np. So you can see e to the power x is np, so my expectation value comes out to be np. Now finally let's take k equal to 2. K equal to 2, we'll find out ex square. Ex square is what? Ex square will be np e to the power y plus 1 to the power k minus 1. So this becomes np e to the power. Now to find that out, we can easily see this. So e to the power y will be what? E to the sorry, not e to the power y. Ey will be nothing but n minus 1p. So this term whole comes out to be np into n minus 1p plus 1, right? So this becomes np into np plus 1 minus p, right? Let's now do the variance. So where x will be what? So it will be np whole square plus np minus np square minus ex squared, so that will be np whole squared. So this and this gets cut, so this becomes, we take np common, it becomes 1 minus p. So you see, it's nothing but finally you find out to the expectation to be nothing but n into p, and the variance of x to be n into p into 1 minus p, means the probability of 0, probability of 1, and here it is the probability of 1 only. Okay, so this is how we find out the value of expectation and variance in the case of binomial. So now let's talk about a very interesting result. So let's say if you plot pk and k, okay, in the case of this, so people have seen it monotonically increases first, reaches a maximum value, and then monotonically decreases. Okay, so I am telling you how do you find this value of k where it is the maximum value. Okay, so let's now try to empirically find that out. So let's say pk, and we will find out pk minus 1. So what is pk? Pk is nck p to the power k, p1 minus p to the power n minus k, nck minus 1, pk minus 1, 1 minus p, n minus k plus 1. So finally, I'm not doing the big calculation, you can do it on your own. After doing the calculation, you'll find it is n minus k plus 1 by k into p by 1 minus p. Okay, so so we need to find out, so we initially know it is monotonically increase, then we have to see where it decreases, right? So if it is decreasing, so we are considering this value to be pk minus 1, and this, let's say this value to be pk. So you have to see that pk is your has to be less than equal to pk minus 1, that is this case, right? Or maybe let's take the reverse thing. Okay, so let's say this is pk, and the just before it, it's pk minus 1. Okay, so here we find this out that p for every, this is true for pk greater than equal to pk minus 1. So pk greater than pk minus 1 would become what? Pk by pk minus 1 greater than equal to 1, or n minus k plus 1 by k into p minus 1 minus p, which is greater than 1, right? So now let's calculate this. So this becomes what? Np minus nk plus p greater than equal to k minus kp, right? Can we do this? Yes, it is. We can do this. Now if you have to take k common, take the k terms this side, so this will be n into, sorry, p into n plus 1, and we'll get k here, k minus kp plus nk. Okay, so k has to be less than equal to p into n plus 1 by 1 minus p plus n. You get this big term here. Okay, so now if you synthesize this, right, if you synthesize this value actually comes out to be k less than equal to n minus n plus 1 into p. Okay, I might have done some silly mistake here if I am not wrong, because the answer is supposed to come like this. I think I have done some silly mistake or something. So nk kp. Okay, this has to be kp. Sorry, this is kp. So this would also be kp, and this gets cut. Yes. So this is wrong. Sorry. This is a wrong statement. So the final answer comes out to be this. Okay. So in this case, the k's maximum value will be when the value of n plus 1 into p, and when we get the actual biggest value of k here. Finally, the last thing we can do is how to empirically find the next, like make a algorithm to find all the values. Okay, so how do we find this values? So we try to do this pk plus 1 by pk. So using the earlier logic only, we can find this out to be p by 1 minus p n minus k by k plus 1. So if you calculate this comes out to be this. So if you have pk plus 1 is equal to pk and to p minus 1 into n minus k by k plus 1. So you can actually make an algorithm and find all the next values of this. So start with p0 and then you empirically put the values and you can do it. So usually if you plot the graph, let's say if I do a histogram, it will look something like this. Okay, so something like this. So this is how the binomial graph would look. So with this we have covered binomial today completely, and now we'll cover the rest the next day.